Hey everyone, in this video we're going to be going over section 2.3, calculating limits using the limit laws. Let's dive in, shall we? So first I'm going to start to write down some of these limit laws, and I'm gonna keep them all on one sheet of paper. There's going to be about 9 of them, and I'm going to recommend that you guys put all of the limit laws on one sheet of paper as well. You're going to use them as you go through and do your homework, so it'd be nice if they were all in one place. So let's start. What are the limit laws? Well, first off, let's suppose, limit laws. Let's let C be some real number. That says let C be in R. That translates to let C be any real number. So let C be in R, and let the limit as x go to a of f of x, and the limit as x go to a of g of x exist. Cool. So we've got a real number c, and we've got these two limits. They go to the same point, and we've got these two functions, and these limits exist. So a refresher from last time, that means the limit from the left as x approaches a of f of x has to be equal to the limit from the right as x approaches a of f of x, and the same thing holds for g as well. So these limits exist, and now we've got some results. The first limit law, we'll say then, the first limit law, if we take the limit as x approaches a of f of x plus g of x. So now the limit of the sum of these functions is equal to the sum of the limits. The limit as x approaches a of f of x plus the limit as x approaches a of g of x. Once again, I'm switching from cursive to print. Those are the same f's. All three of those are the same f's. So you'll hear the limit of the sum is equal to the sum of the limits. Our next rule is the limit as x approaches a of some constant times the function f of x. Well, this'll be a new concept that we will explore in greater detail later. This limit only cares about x. So this constant term, that has no bearing really on what this limit is looking for. This limit only affects things that have x's in them. So that means constants we can pull out front in front of limits. So the limit of a constant times some function of x is equal to that constant times the limit as x approaches a of f of x. It's almost like you factored it out, but it's not really factoring. The fact that you can pull something out in front is similar to factoring. It's not truly factoring. The third limit law, the limit as x approaches a of the product of f of x times g of x. The limit of the product is equal to the product of the limits. The limit as x goes to a of f of x times the limit as x goes to a of g of x. And for now, our fourth limit law is the limit as x goes out to a of f of x divided by g of x is equal to the limit as x goes out to a of f of x divided by the limit as x goes out to a of a g of x. This one has an extra rule. This is provided that g of x does not equal 0, because we can't divide by 0. G of x cannot be the constant function 0. So, these are our four, for now, these are our four first limit laws. I've got plus, it can be plus or minus. The limit of the sum is equal to the sum of the limits, or the limit of the difference is equal to the difference of the limits. We have constants can be pulled out. The limit of the product is equal to the product of the limits. And the division one, the limit of the quotient is equal to the quotient of the limits. And let's explore how we will use these with a graph. So this is example 1. And example 1, I believe I already have up on Blackboard. If you guys would like a copy of that graph, you can shoot me an email. So the first thing we want to do is, so this is our function f of x down here, and this is our function g of x. F of x has this break in it, and g of x kind of goes up like a line, curves around, and goes down. So the first thing we want to do is we want to calculate the limit as x approaches 3 of f of x minus 2 g of x. Well, we might have space. So we'll work out a. I want to make sure I'm recording. It's already been a long morning. So a. The limit as x approaches 3 of f of x minus 2g of x. So the first step, or the first thing you want to do, is you want to use the limit laws to help break these things down. Because we can figure out what the limit of f of x is and g of x, but when they're combined like that, that's when you use your limit laws to help break them apart. So, what the first limit law says is we can break this limit up at addition or subtraction. Okay, so this thing is going to be equal to, and I'm going to run out of space if I write here, so you'll have to excuse me. I will do this over here. The limit as x approaches 3 of f of x minus 2g of x, well, we're going to break it up at subtraction, is equal to the limit as x approaches 3 of f of x minus the limit as x approaches 3 of 2g of x. And that was using limit law 1. Limit law number 1. So now we can just find the limit as x approaches 3 of f of x. But now let's deal with the limit as x approaches 3 of 2 times g of x. Well, constants you can pull out in front of limits. That's what limit law 2 is getting at. Constants can be pulled out. So this is equal to the limit as x approaches 3 of f of x minus 2 times the limit as x approaches 3 of g of x. Now that we have broken it apart, I use the term accordion, we have pulled this thing apart, now we can go to our graph. The limit as x approaches 3 of f of x. Well, here's f of x, and as our values of x get really close to 3, the value of f of x is going to approach 2. So, the limit as x approaches 3 of f of x is going to be equal to 2. Now, from that, we're going to subtract 2 times the limit as x approaches 3 of g of x. Well, here's g of x. As x is getting close to 3, g of x is getting close to 3. Limits have to go from both sides. As we approach 3 from the left, g of x is still approaching 3. So, I meant to point at 3 over there. So, the limit as x approaches 3 of g of x is equal to 3. At this point, we're done with calculus. This is now an algebra problem. All you have to do is simplify to get to the correct answer. Well, 2 times 3 is equal to 6, and 2 take away 6 is negative 4. So, the limit as x approaches 3 of f of x minus 2 times g of x is equal to negative 4. So, let's tackle b. That was a. This is going to be b. Let's talk about what happens if we take the limit as x goes out to 2 of f of x times g of x. Well, using the limit laws, we're going to break this limit apart. The limit laws say that the limit of the product is equal to the product of the limits. So that means this is going to be equal to the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. Perfect. We have broken this limit apart into 2 smaller pieces, and now we can refer to this chart or this graph to get the values that we need. So, well, you guys might already see an issue. I'm going to start with g of x. The limit as x approaches 2 of g of x, well, we got to go both directions here. As we approach from the right, it's equal to 2, and as we approach from the left, it's equal to 2. So we know the limit of g of x as x approaches 2 is 2. But f of x, there's this issue. A limit only exists if the limit from the left is equal to the limit from the right. Well, the limit of f of x as x approaches 2 does not exist. Does not exist. Since this limit does not exist, this limit as a whole does not exist. Doesn't matter that it doesn't matter that part of this limit exists. Does not exist is kind of like a trump card if you're used to playing spades, or hearts. I'm sorry. Once one of these doesn't exist, the whole thing doesn't exist. You would need both parts to exist in order to get to a number. So, since the limit as x approaches 2 of f of x doesn't exist, that means the limit as x approaches 2 of f of x times g of x does not exist. Cool. So, for the final one, let's talk about the limit, and this is c. The limit as x goes off to 0 of f of x divided by g of x. Well, this is that last limit law coming into effect. The limit of the quotient is equal to the quotient of the limits. Or, that means we can rewrite this as the limit as x goes out to 0 of f of x divided by the limit as x goes out to 0 of g of x. Well, the limit as x approaches 0 of f of x, here's f of x, it jumps. As x gets really close to 0, y is going to 3. But g of x is equal to 0. We can't divide by 0. This limit also does not exist. You can't divide by 0. So we can't say that this limit is equal to a number. If you wind up dividing by 0 after applying this rule, your limit as a whole does not exist. Now, this is not the chart out of the book. This is something I made up, but the answers are similar. If you read this example in the book, the answer to part A gives you a number, and the answer to part B and C do not exist. If this part didn't make sense to you, go look in the book and read over example 1 for section 2.3 and see if another function and a different explanation will help you. Like always, if you have any questions, please do not hesitate to shoot me an email. But yeah, these are our limit laws, and this is how we're going to use them. So let me figure out where I'm at real quick, and let's move on to another example. Sorry about that. As I said, we're moving on to another example. I've got a couple more rules for you, then we'll jump on to the next example. These are going to be some more of our limit laws. The next one is called the power law. The book goes through and gives it a specific name. I'm not too terribly worried with you guys knowing the specific names of all the limit laws. I'm not going to ask you on a quiz or a test to tell me what the power law for limits is. I'm more concerned with you guys knowing how to use the rules. So, that being said, the book calls this the power law. I'm going to call it limit law number 5. This is power law. So, and power law, or the power law, really comes from limit law 3. Well, from limit law 3, it says if we multiply two functions together, that's equal to the product of those limits. So if g of x and f of x were the same thing, this would say f of x squared is equal to the limit of f of x quantity squared. And if we apply that law recursively, what we can get is that the limit as x approaches a of f of x, and this function to some power, well, c is a real number, so we'll say n. I need something else on n. Is equal to the limit as x approaches a of f of x all to the n. Okay, so we have this function. It's got an exponent on it, and it's saying that instead of calculating the limit of this function with an exponent, we calculate the limit and then apply the exponent. So that's what we call our power law. I've got a couple more for you. Well, we've got the limit as x goes to a of some constant. This isn't x, this is that constant c I was talking about. That's just equal to c, and this is our 6th limit law. This one, so remember, this is a function. This is like the line, and this is a side note, this is like the line y is equal to c. And if we were to graph that, here's our xy coordinates. The line y is equal to c is a horizontal line that goes through the point 0, c. And now, it doesn't matter what the value of a is. If we say, put a right here, take a look. As we approach, as we let some point slide left and right on this graph, as this point gets closer and closer and closer to having an x value of a, its y value is always c. It's moving on a horizontal line. Similarly, as we approach from the other direction, as we let this point slide in from that direction, as its x value gets closer and closer to a, its y value is always c. So, the limit as x approaches some number of a constant is equal to that constant. For 7, the limit as x approaches a of just x is equal to a. We've got a couple more. Let's call this 8. The limit as x goes off to a of x to the n is equal to a to the n. 8 is very similar to that power law. And then 9 is also similar to the power law. The limit as x approaches a of the nth root of x is equal to the nth root of the limit as x goes off to a of x. And by nth root, what do I mean? That's like the limit as x goes off to a of the cubed root of x is equal to the cubed root of the limit as x goes off to a of x. That's what I mean by nth root. We could put a 3 here, we could put a 4 here, a 5 here. If we don't write anything, there's an implied 2 and we get just the plain old square root. But for any number you put here, you can also put it there. And this one goes one step further. Let's see. We do have to say that if n is even for this one, that'd be like a square root or a fourth root. A has to be bigger than or equal to 0. Because you can't wind up taking the square root of -2 or the square root of -4, because we're only talking about real values here. So if n is even, a has to be positive. In this one, n is odd, so a can be any real number. And the last one I'll give you is really just a continuation of 10. The last one for now, at least. 10 is the limit as x goes off to a of the nth root of some function of x. And I'm sorry, I bet you guys are stuck listening to whatever's going on outside all lecture long. I apologize. Is equal to the nth root. I don't know why I wrote 11 there. The limit of the nth root of f of x is equal to the nth root of the limit as x goes off to a of f of x. These are going to be our limit laws. We might have one or two more, but for now, these are the 10 that we're going to use to actually solve some limits. So I've got two examples for you now. So we're going to calculate the following limits. Let's calculate the limit as x goes off to 5 of the polynomial 2x squared minus 3x plus 4. And what we want to do is we want to use our limit laws to break this thing apart and calculate the limit. So using our limit laws, let's break this up at addition and subtraction first. This is going to be equal to the limit as x goes off to 5 of 2x squared minus the limit as x goes off to 5 of 3x plus the limit as x goes off to 5 of 4. Okay, so now let's pull out all of our constants. This is going to be equal to the limit, this is going to be equal to 2 times the limit as x goes off to 5 of x squared minus 3 times the limit as x goes off to 5 of x plus the limit as x goes off to 5 of 4. Perfect. This one's something we can take care of. We've got a limit law to take care of this one. The final step is to use one more limit law here and say that this is equal to 2 times the limit as x goes off to 5 of x quantity squared minus 3 times the limit as x goes off to 5 of x plus the limit as x goes off to 5 of 4. Perfect. Now all of these are set up for us to use a limit law on. This 2 is going to fall down. We have in brackets the limit as x approaches 5 of x. Well, the limit as x approaches, the limit of x as x approaches a is a. That means the limit of x as x approaches 5 is 5 squared minus, once again, the 3 times the limit of x as x approaches 5 is 5 plus, and now we have this law. The limit as x approaches a of a constant is equal to that constant. So the limit as x approaches 5 of 4 is equal to 4. At this point, there's no more calculus. It is an algebra problem. We have 2. 5 squared is 25 minus 15 plus 4 equals 50 minus 15 plus 4. 50 take away 15 is 35 plus 4 is 39. You guys are in calculus now. I largely don't care about anything beneath that line. I'm going to make sure you get the right answer, but at this point I trust that you guys can do your algebra. If you make a mistake, mistakes in algebra happen. They're like typos, they're like little misspelling errors because you hit the wrong key. Algebra mistakes happen. I will always be primarily concerned with your calculus. And your algebra will always be a secondary consideration of mine. You have to do it correct to get the right answer, but I will mostly be grading you on this chunk, but that chunk will always weigh in on your grade as well. So we used our limit laws, we broke down the problem, we got to 39. Wonderful. Let's try this on another problem. This one over here. Let's say we wanted to take the limit as x approaches negative 2 of x cubed plus 2x squared minus 1 divided by 5 minus 3x. Perfect. So the limit of the quotient is going to equal the quotient of the limits, provided that the denominator doesn't equal 0. So we're going to break this thing up and call this the limit as x approaches negative 2 of x cubed plus 2. I don't want to cramp myself on this problem like I did the last one. This thing is equal to the limit as x approaches negative 2 of x cubed plus 2x squared minus 1, all divided by the limit as x approaches negative 2 of 5 minus 3x. Also, the homework problems you do in calculus are probably going to take up much more real estate on your paper than they have so in previous classes. I would strongly discourage you guys from trying to fit an entire calculus assignment on one piece of paper. Use multiple pieces of paper and please keep your work organized. But yeah, if your problems are getting long and big, that's to be expected. So we took the limit of the quotient, turned it into a quotient of the limits. Now we're going to break everything up at addition and subtraction respectively. We'll call this the limit as x approaches negative 2 of x cubed plus the limit as x approaches negative 2 of 2x squared minus the limit as x approaches negative 2 of 1, all divided by the limit as x approaches negative 2 of 5 minus the limit as x approaches negative 2 of 3x. I am now going to go through and apply all my limit laws. I'm gonna apply 2 here at the same time. Turn this into the limit, or we'll turn this into the limit as x approaches negative 2 of x, quantity cubed, plus 2 times the limit as x approaches negative 2 of x quantity squared minus the limit as x approaches negative 2 of 1. All of that divided by the limit as x approaches negative 2 of 5 minus 3 times the limit as x approaches negative 2 of just an x. There we go. 2 steps away from the final problem. The limit as x approaches 2 of x is equal to negative 2. I'll say that again because I said that poorly. The limit as x approaches negative 2 of x is equal to negative 2. So we will get negative 2. It's going to be cubed. Plus 2 times, same thing, the limit as x approaches negative 2 of x is equal to negative 2 squared, because that's squared, minus the limit as x approaches negative 2 of a constant is equal to that constant, minus 1, all divided by the limit as x approaches negative 2 of a constant is equal to that constant, minus 3 times the limit as x approaches negative 2 of x is negative 2. This is where your calculus ends. The final step is to simplify. Negative 2 cubed is negative 8. That's going to be 4. 4 times 2 is another 8 minus 1 all over 5 plus 6 gives us 11. Those will cancel and we're left with negative 1 over 11 for a final answer. Feel free to skip some steps in your algebra. I don't need to see every little step of your algebra. If you get the wrong answer because of an algebra error, I'm probably going to take a half a point. That's kind of my standard deduction, if you will. If you guys do all the calculus correctly, if you did everything correct up to this point, and you said the answer was negative 2 over 11 or something like that, that'd be a half a point on probably a 3-point problem. So, using our limit laws. And now there was something that you might have noticed. Let me start recording again. Cool, there's something that you might have noticed. This function, x cubed plus 2x squared minus 1 divided by 5 minus 3x, is defined when x is equal to negative 2. And if we were to just plug x is equal to negative 2 into that function, well, it would equal negative 1 over 11. That gives us what we call the direct substitution property. What the direct substitution property says is that, oh, I got a typo over here. It says, and we'll call this the direct substitution property. So it says, if f is some polynomial function, is a rational polynomial function, and a rational polynomial function is some polynomial function p of x that has a numerator, we'll call it q of x, and a denominator, pqr of x. So it's some polynomial function, q of x divided by r of x. So if f is a polynomial function, that we'll say if f is a polynomial function and some constant and c is in the domain of f, then you can just plug it in. The limit as x approaches c of f of x is equal to f of c. The direct substitution property. So let's look at a picture. Here's a picture of what's going on. So g of x is some polynomial function. And if you look, 2 is in the domain of g of x. You can tell that 2 is in the domain of g of x because there's a dot on its graph for g of x. Well, the limit as x approaches 2 from the left and the limit as x approaches 2 from the right is equal to the function evaluated at 2 because 2 is in the domain of that function. What's a picture? Let's do this function. We'll say that we have, we'll say f of x is equal to x squared plus 1 if x is different than 0. So, what this looks like, this is a parabola. Let's see. Let me come up with a different example off the top of my head. Cool, so let's do an example. Let's say we wanted to find the limit as x approaches 1 of x squared minus 1 over x minus 1. Now if you look, this function isn't defined when x is equal to 1, so we cannot currently use the direct substitution property. But if we factor the numerator, this thing is equal to the limit as x approaches 1 of x plus 1 times x minus 1, all divided by the quantity of x minus 1. We've got the same factor top and bottom. Those will cancel each other out. This is equal to the limit as x approaches 1 of x plus 1. Now, we could use our limit laws and we could break it up at addition, but x plus 1, if you notice what the rational polynomial function is saying, c is in the domain of f. 1 is in the domain of x plus 1. It's a line, it's a polynomial, it's defined everywhere. Since 1 is in the domain of this function, we don't have to use our limit laws. We can break this up and just plug the value of 1 in and get 1 plus 1, which is equal to 2. Once that value, this value at the bottom of the limit, is in the domain of this function, you can directly plug it in. That's why we couldn't do it here, because we can't divide by 0. Another note, notice how I wrote the limit at every step. You have to write the limit at every step until you evaluate the limit. The limit is kind of like in a plus sign, a minus sign. It's an operation, it's a command, it's telling you to do something. The limit as x goes to 1 of x squared minus 1 over x minus 1 is not equal to x plus 1, but it is equal to the limit as x approaches 1 of x plus 1. You need the limit until you evaluate the limit, and once the number that you're limiting to is in the domain of the function, you can just directly plug that value in. So now for a theorem. Let's say we've got two functions. We've got a function f of x and g of x. So if f of x is equal to g of x everywhere except 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 when x is equal to a. then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. Okay. So we have these two functions, f of x and g of x. They are exactly the same everywhere except for at one point. So I am going to, let's draw a picture of this. So with my pen, I'm going to draw f of x. F of x is going to be this parabola. And we're going to call this point A, and we're going to call this value capital L. And this is our f of x in blue pen. G of x is going to be in a Sharpie. G of x is going to look like this. Okay, so you can't see f of x for the most part anymore, but f of x was this nice parabola, and g of x was almost the exact same as f of x, except for at this point, when x is equal to a, g of x jumps. It has this value up here for whatever reason. But now take a look. If we talk about the limit as x goes to a of f of x, well, as x goes to a of f of x in both directions, that function limits to L. Same thing with g of x. Limit as x goes to a of g of x. Well, g of x goes to L. So if you've got two functions that are identical everywhere except for at a point, the limit as they approach that point is going to be the same. Let's see. What will be our next example? Perfect. Let me get a new piece of paper. You know, before I go and get another piece of paper, I do want to say one more thing about this problem. And you know, I probably should have found my other page before I started talking. It's fine. We did a problem that was x squared minus 1 over x minus 1, and we took that limit as x went off to 1. We did it 5-10 minutes ago. So the reason why this theorem kind of gives reason to why we were able to say the limit as x goes to 1 of x plus 1. These two, and if you were to graph these, I'd graph them in Desmos. I graph everything in Desmos because it's colorful and free. If you were to graph these two functions without their limit, they look exactly the same. This thing looks like the line x plus 1, except for it has a hole at the point x is equal to 1. So this theorem is really giving us a justification for why we can simplify polynomial functions and then just evaluate the limit. That just occurred to me. I wanted to say that as some teaching note. We will jump forward to another example, so I don't write in Sharpie because it bleeds. So, let's evaluate this limit. The limit as h goes to 0, and you don't know it yet, but this is going to be a very common thing for us, letting h go to 0, of 3 plus h quantities squared minus 9 all over h. So at this point, what you're trying to do, why we talked about that direct substitution, is that what I called it? Why we talked about this theorem is we can't, let me backtrack. Answering limits, solving limits are the easiest, they're most simple when we can use the direct substitution principle. When you can just plug that number into a limit and get a number out. That's our goal, to be able to use the direct substitution principle. The thing is, we will have to use this theorem in order to make it so that value is in the domain of this function. What do I mean by that? This theorem says that we can algebraically manipulate this thing to our heart's content as long as we don't break the rules of mathematics, with the goal of being able to just plug that number in somehow. So let's see what happens. If you get tasked with, and you will be tasked with solving limits, I assign you homework. If you can't directly plug that value in, and I keep on pointing at the denominator because we can't divide by 0. If you can't just plug that value in, then algebraically manipulate this thing. Well, this is equal to the limit, and you have to write the limit every step until you evaluate the limit. Well, 3 plus h squared. Use your distributive property. I have no doubt, because students always do that, you can't distribute a squared over. This is definitely not equal to 9 plus h squared. You have to use your distributive property to get 9 plus 2h plus h squared. This is one I'm usually not too strict on algebra mistakes. This is one mistake I am pretty strict on. I'm very lenient on it until I am teaching calculus, and by the time I'm in calculus, I say you guys need to break yourself of this habit. This is definitely worth more than a half a point off if I see you guys say 3 plus h quantity squared is 3 squared plus h squared. You need to use your distributive property. Don't make that mistake. Break yourself of that mistake. Remind yourself that you need to use the distributive property when you are squaring binomials. Whatever it takes, but just remember that you cannot distribute a squared over addition or subtraction. You got to use your distributive property. Okay. So, distributive property says numerator becomes 3 plus, and I misspoke here, that was supposed to be a 6. 3 plus 6h plus h squared minus 9 all over h. And I misspoke again. That's a 9. If you actually use your distributive property, you'd probably make fewer mistakes than I just did. 3 times 3 was 9. 3 times h gave us 3h. h times 3 gave us another 3h for 6h, plus h times h for h squared. I'm not going to require you to show your work, but it's really easy to make a mistake if you don't show your work. I just said I won't require you to show your work. I want to say something about that. I'm not going to force you to show me all the algebra because we're in a calculus class. You need to show me enough work that I know that you aren't just copying these things online. But you don't have to show me every little detail. At this point, we've got an h in a numerator, h in a denominator. Let's factor an h out of our numerator. The limit as h goes off to 0 of h times 6 plus h divided by h. These h's will cancel, equals the limit as h goes off to 0 of 6 plus h. Perfect. Finally, 0 is in the domain of that function. Since 0 is in the domain of that function, we can use the direct substitution principle and say this limit is just equal to this function evaluated at that point. Equals 6 plus 0 equals 6. So we couldn't directly plug in the value or the point at which we are trying to limit into the function because the function isn't defined at that point. So we algebraically manipulate it. We correctly algebraically manipulate it. We use our distributive property correctly, and we got rid of our constants. We factored out a h, and we used the h in the numerator to cancel out the h in the denominator. You guys don't know it yet, but this is pretty much what Chapter 3 is dedicated to, being able to factor an h out of a numerator and cancel it with an h in a denominator. You will see this again and again and again. But for now, it's just an exercise, if you will. We don't have meaning for it yet. But that was our goal. Let me restart recording real quick, and we will do another example. Okay, so that was example 5. This will be example 6. I don't have a graph or anything for it. I'm just numbering it Helps me stay organized. And I have to keep on chopping the video in between examples. The camera I used to record this will only record a 10-minute segment at a time. I think I've changed that to 30 minutes. I can't remember. I've just been burnt in the past by my camera, and I've recorded long lectures to realize that I only got the first 10 minutes. It's been a painful experience. Let's take the limit as x goes off to 0. I'm switching to x's. Of the square root of x squared plus 9 minus 3 all over x squared. So, right now, we can't plug x equals 0 into this function because it's not defined when x is equal to 0. We still want to use our direct substitution. Now we need to come up with some way of algebraically manipulating this thing in order to get what we want, in order to manipulate it to make it so we can just plug 0 in. So this is incredibly tricky to deal with. There's not really an easy way to break apart the square root of x squared plus 9. What we can do is we can rationalize the numerator. That's a y. That's totally a y. Kind of like in, not Diffie-Q, trigonometry. In trigonometry, how if you were to take, say, the sine of pi fourths, some resources call that 1 over the square root of 2, and students would multiply by the square root of 2 divided by the square root of 2, turn that into the square root of 2 divided by 2. In trigonometry, you are rationalizing the denominator. Well, what we are going to do is we are going to rationalize the numerator. I'm going to put that in a box. What we want to do is we are going to multiply the numerator, top and bottom, by the square root of x squared plus 9. That part hasn't changed, plus 3. Same thing, top and bottom. I drew a big plus sign to show you that this thing is switched. The sound effect made my pen go faster. The operation has switched. Okay? That's the factor, that's the thing you want to multiply top and bottom by. You take the numerator, you change only that sign stayed the same, and those two stayed the same. Now, when you use the distributive property on this thing, this limit, I'm just going to drop down. Okay. So now, our numerator, when we do the square root of x squared plus 9 times the square root of x squared plus 9, that'll just give us x squared plus 9. Now we'll do plus 3 times the square root of x plus 9 minus 3 times the square root of x plus 9. I'll write it out. Plus 3 times the square root of x squared plus 9 minus 3 times the square root of x squared plus 9. And then negative 3 times a positive 3 will give us minus 9. All that is going to be divided by the product of x squared and the square root of x squared plus 9 plus 3. Some algebra. Alright, I gotta pop my knee. Okay. So we've got 3 of the square root of x squared plus 9s and a negative 3 of the square root of x squared plus 9s. They cancel. This negative 9 and that positive 9 are also going to cancel. And finally, this x squared in the numerator is going to cancel out with this x squared in the denominator. And they're going to cancel. We have canceled everything out of the numerator. What is our new numerator? It's 1 all over our denominator. The square root of x squared plus 9 plus 3. Plus 3. You might go, what do you mean it's 1? A lot of times students are going to want to put a 0 right here. And I encourage you, what is, say, x divided by x squared? When you cancel everything out of the numerator, you get 1 over x. Or what about x plus 1 over x squared minus 1? Well, you can factor the denominator, x plus 1 over x plus 1, x minus 1. You cancel everything out of the numerator. You're left with 1 over x minus 1. So we canceled everything out of the numerator. Those two simplified to 0. Those two simplified to 0. We canceled the x squared in the numerator with an x squared in the denominator, and our numerator became 1. All over the quantity of the square root of x squared plus 9 plus 3. Perfect. Whenever you simplify, whenever you do an algebraic step, like we couldn't plug x equals 0 in, we did some algebra, we simplified. This is our next sort of stable platform to stand on. Nothing's moving, we're no longer simplifying, we've just got a nice foundation to relax on. Always see if you can plug that limit back in. The second you find a stable platform to stand on, see if you can plug that limit in. And we can totally let x be equal to 0. This is equal to 1 over the square root of 0 squared plus 9 plus 3. 0 squared plus 9 is equal to 9. The square root of 9 is equal to 3, which equals 1/6 for our final answer. On your homework, I like boxes on final answers, circles on final answers. I don't think I have boxed or circled a final answer up until this point. It's not required. I'm not going to require anything of you. I won't do. But I do like boxes or circles around your answers. That helps me. But rationalize the numerator. So I got a couple more examples for you. It was my intention to keep this lecture a little short. So let's talk about the limit as x goes off to 0, absolute value of x. And we want to show that the limit as x approaches 0 of the absolute value of x is equal to 0. Okay, so this is kind of a refresher. In order to do that, we want to take the limit as x goes to 0 from the left of the absolute value of x. And there's two ways to think about it. One, you can think, if you're a graphical person, the absolute value of x looks like this. Well, the limit as x approaches 0 from the left is going to be equal to 0. If you're an algebraic person, we'll tackle the limit as x approaches 0 from the right of the absolute value of x. We'll tackle this one algebraically. Well, the definition of this function is equal to the limit as x approaches 0 from the right of, we have x if x is positive, or negative x if x is less than 0. Well, as we approach x from the right, it's always going to be positive. Well, if it's always going to be positive, but it's getting smaller and smaller and smaller, we're going to 0. Since the limit from the left matched the limit from the right, we were able to show that that limit was in fact equal to 0. But now, we want to show that the limit as x approaches 0 of the absolute value of x divided by x does not exist. So for this one, I'm going to completely solve algebraically. To show that the limit doesn't exist, we need to take the limit from the left and from the right. The limit as x approaches 0 from the left, the absolute value of x divided by x. Well, x is always going to be a negative number. Since x is always going to be negative, we can substitute negative x in for the absolute value of x. This is equal to the limit. You have to write the limit every time until you evaluate it. Negative x over x. Well, that's equal to the limit as x approaches 0 from the left. Negative x divided by x is -1, which equals -1. Okay? Once again, we're approaching we're approaching 0 from the left. If you're to the left of 0, you're always negative. So that's why we were able to make this substitution. Similarly, if we took the limit as x went out to 0 of the right, the absolute value of x divided by x, well, all the numbers to the right of 0 are positive, so we can replace the absolute value of x with just a plain old x. X over x simplifies to 1, and the limit of 1 as x approaches 0 from the right is 1. Since the limit from the left did not equal to the limit to the right, we know that this limit as a whole does not exist. Okay, let's see what's next. Cool, so I've got 2 more examples in an almost dead battery, so let's, moving quickly, this is example 9. We want to see if the limit exists. We want to determine if the limit as x approaches 4 of f of x exists, provided that f of x is equal to the square root of x minus 4 if x is bigger than 4, and 8 minus 2x if x is less than 4. Notice how our function is not defined when x is equal to 4. It's fine. So if this limit exists, how do you know if a limit exists? Well, a limit exists only if you approach the value, and I'm frantically looking for a graph, only exists if you approach the same value from the left and from the right. Here's a smaller version of the chart. So, a limit only exists if the limit from the left equals the limit from the right. So, in order to see if this limit exists, we have to see what the limit as x approaches 4 from the left of f of x is. Well, as we approach 4 from the left, think about it on a number line. If here's 4, from the left is like 3.9, and from the right is like 4.1. From the left, all the numbers are going to be less than 4. Okay? So we're looking at this part of the piecewise defined function. And this is just a line. 4 is in the domain of this line, so we can directly substitute. We can use our direct substitution principle. This is going to be equal to the limit as x approaches 4 from the left of 8 minus 2x, which by the direct substitution principle is equal to 8 minus 2 times 4, which is equal to 0. Solid. Let's go the other direction. Let's take the limit as x approaches 4 from the right of f of x. Well, from the right, all these numbers are bigger than 4, so we're going to use this part of the piecewise defined function, which is equal to the limit as x approaches 4 from the right of the square root of x minus 4. Sweet. Well, once again, this thing is defined when x is equal to 4. You can take the square root of 4 minus 4, or you can take the square root of 0, because the square root of 0 is equal to 0. Now, if you see what we've got the limit from the left is equal to the limit from the right. So this limit exists, and the limit as x approaches 4 of f of x is equal to 0. If you're tasked with determining if a limit exists, take the limit from the left, take the limit from the right, and see if those things are equal. Okay. So in the interest of time and in the interest of my batteries dying, we're going to skip over what the book calls example 10, what I call example 10. It's the greatest integer function. I would encourage you guys to read over it. It's nothing you haven't seen already. The book says the theorem, and then they generalize their theorem, and we get to the squeeze theorem. Cool. So we're going to assume that we have three functions. We're going to have f of x, g of x, and h of x. And I'm going to assume that for all values of x, except where x is equal to a, if f of x is less than or equal to g of x, which is less than or equal to h of x, and the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, which we're going to call some letter L for the sake of argument, then the limit as x approaches a of g of x is equal to L. So we've got these functions, f of x, g of x, and h of x. F of x is smaller than g of x, which is smaller than h of x. But these two things have the same limit. That means the thing in the middle has to have that limit. This is going to be example 11. Example 11 is actually going to have a graph. It's going to be on Desmos, and the link is on Blackboard. But I want to say a couple things before I cut over to the laptop. We're going to talk about the limit as x goes off to 0 of x squared times the sine of 1 over x. And we're going to do this on the back. So, to use the squeeze theorem, we need to come up with a function that's always greater than this and a function that's always less than this. Now, here's the trick. Whatever value you feed sine, -1 is less than or equal to the sine of x, which is less than or equal to +1. This provides both an upper and a lower bound for the value of sine of x, or for the value of 1 over sine of x. Regardless of what you put inside here, sine of x is always going to kick you out some number between -1 and 1. So that means -1 times x squared has to be less than or equal to, we'll say x squared times the sine of 1 over x, which has to be less than or equal to 1 times x squared. That's an x, and that's a 1. So the smallest value sine of 1 over x can have is negative 1, and the biggest value sine of 1 over x can have is positive 1. So that means this thing, x squared sine of 1 over x is bounded from beneath by a negative x squared less than or equal to x squared sine of 1 over x, which is less than or equal to a positive x squared. And now the reason why we do this, the only thing we care about is the value of this limit, and we've done all this other work off to the side. But by the squeeze theorem, and we know this is a much easier limit to calculate. We know that the limit as x approaches 0 of negative x squared, well, negative x squared is defined when x is equal to 0, so that equals 0. Similarly, the limit as x approaches 0 of x squared, well, this is defined at x squared. That 2 is also equal to 0. So we have some f of x. We know that f of x, which is equal to x squared, is less than or equal to x squared times the sine of 1 over x, which is less than or equal to some g of x, which I'll call x squared, and I'll go back and I'll put a minus sign over here to make it less confusing for you guys. We got an f of x, it's equal to negative x squared. We've got this thing in the middle, and we've got this g of x, and that's equal to a positive x squared. We know that the limit as x approaches 0 of f of x is equal to 0, and we know that the limit as x approaches 0 of g of x is equal to 0. That means this thing in the middle, the limit as x approaches 0 of x squared sine of 1 over x, also has to equal 0 for our final answer. We were able to squeeze this function in between these two functions. So I'm going to cut over to my laptop. I've got this animated, and I want to show you what also is going on. Before I do that, I don't want to cut back. This is our final example. Your guys' homework, it's already up on Blackboard. I like to write it in the video. Is going to be 11 through 31 odd. And then 37 and 39. Okay, these squeeze theorem problems, they're tricky to come up with lower and upper bounds. Focus the majority of your efforts right here, but definitely don't not do those. Okay, so let me cut over to my laptop real quick. Okay everyone, so here we are at Desmos, and I have just been made painfully aware that I used f of x, g of x, and h of x in this problem, and I used them with what I wrote on the page, and I bet I've called something different. I bet I either have h of x wrong or g of x wrong. But this is what I want to show you. This thing in green is the curve we care about, and we don't care about those labels right now. This green wiggle is x squared times sine of 1 over x. And this thing is going to oscillate. It's going to oscillate infinitely fast near x is equal to 0. It's like, oops, not that button. It's like this graph over here. How we had the sine of pi divided by x, how it oscillated infinitely fast near the origin. Same thing's going to happen. Let's go over here. And in fact, if we take off everything but here, and then there we go. So this thing in blue is our point, and we want to see what happens to the y value. And can we slow you down some? Well, the y value is never going to settle down. It does that quick oscillation, and the program rounded it to 0. But we're still oscillating. We're still bouncing back and forth. You can see the closer and closer I zoom in, we're still oscillating. We're still going up and down. I have lost the origin. We're still wiggling. It's hard to tell. So that's why we use the squeeze theorem. We use the squeeze theorem because the limit of x squared and the limit of negative x squared is a whole lot easier to calculate by themselves as compared to the limit of x squared times the sine of 1 over x. And the reason why we chose those is because, let me put f of x and let me put g of x on there. You can see the curve that we care about is always bounded between these two curves. They agree in points. They agree f of x and h of x. And I'm using these definitions of f, g, and h. F of x and h of x agree at this point, and they agree at this point, but h of x is always beneath f of x. Similarly, h of x and g of x, they agree at that point and that point, but that h of x is always in between those two curves. It's always, always, always bounded by them. So, if this top curve, if that y value limits to 0 as x is getting closer and closer to 0, and it does, it limits, and on bottom it limits, and it does, then, since this thing is sandwiched in between the two, that means that it too is also going to limit to 0. Got a bunch of, you can kind of see that if I do this. We'll need our labels on. So we know the behavior of this purple point and this red point. Let's at least make those match in color. Let's make that red. Let's make that green. Let's make that blue. Okay. So the top is limiting down, the bottom is limiting kind of up, and green is stuck bouncing between the two. So that's what the squeeze theorem is saying. We try and come up with two functions, one that's always on top of a function, one that's always on bottom, and then we want to take their limit. The trick is you want these two things to limit to the same point. If I shifted that top graph up by 1, and I'm zoomed so far in that it jumped off screen, if I shift that top graph up by 1, it squeezes our theorem, but it doesn't give us any meaningful information. So, this is what the squeeze theorem is talking about. It's talking about sandwiching curves and using the upper and lower curve to gain information about the middle curve, the contents of your sandwich. Coming up with these curves can be rather difficult. I believe in your homework you are provided with the appropriate curves. Just be aware that this theorem exists. And it's quite powerful. It gets used in mathematics a lot. With that, that's all I have prepared for you guys today. Your homework is already up on Blackboard. It's 11 through 31 odd, 37, and 39. Class will be canceled on Monday because it's Memorial Day. You guys stay safe and healthy, and I will talk to you again on Wednesday. Talk to you later. Bye-bye.